In mathematics, Hurwitz's theorem is a theorem of Adolf Hurwitz, published posthumously in 1923, on finite-dimensional unital real non-associative algebras endowed with a positive definite quadratic form. The theorem states that if the quadratic form defines a homomorphism into the positive real numbers on the non-zero part of the algebra, then the algebra must be isomorphic to the real numbers, the complex numbers, the quaternions or the octonions. The non-associative algebras occurring are called Hurwitz algebras or composition algebras. The problem has an equivalent formulation in terms of quadratic forms Q. Composability requiring the existence of a bilinear composition Z such that QQ equals Q. Subsequent proofs have used the Cayley-Dickson construction. Although neither commutative nor associative, composition algebras have the special property of being alternative algebras, i.e., left and right multiplication preserves squares, a weakened version of associativity. Their theory has subsequently been generalized to arbitrary quadratic forms and arbitrary fields. Hurwitz's theorem implies that multiplicative formulas for sums of squares can only occur in 1, 2, 4 and 8 dimensions, a result originally proved by Hurwitz in 1898. It is a special case of the Hurwitz problem, solved also in radon. Subsequent proofs of the restrictions on the dimension have been given by Ekman using the representation theory of finite groups and by Leon Chevalier using Clifford algebras. Hurwitz's theorem has been applied in algebraic topology to problems on vector fields on spheres and the homotopy groups of the classical groups and, in quantum mechanics, to the classification of simple Jordan algebras. Euclidean Hurwitz algebras. Definition: a Hurwitz algebra or composition algebra is a finite-dimensional, not necessarily non-associative algebra with identity endowed with a non-degenerate quadratic form Q such that Q equals QQ. If the underlying coefficient field is the rails and Q is positive definite, so that equals 1/2 Q minus Q minus Q is an inner product, then A is called a Euclidean Hurwitz algebra. If A is a Euclidean Hurwitz algebra and A is in A, define the involution and right and left multiplication operators by evidently the involution has period 2 and preserves the inner product and norm. These operators have the following properties. The involution is an anti-automorphism, i.e., asterisk equals B asterisk or asterisk. A asterisk equals A 2 1 equals R asterisk A, L equals L asterisk, R equals R asterisk, so that the involution on the algebra corresponds to taking adjoints. Re equals Re if Re x equals 2 equals 1, Re c equals Re A, L equals L2, R equals R2, so that A is an alternating algebra. These properties are proved starting from the polarized version of the identity equals. Setting B equals 1 or D equals 1 yields L equals L asterisk and R equals R asterisk. Hence Re equals 1 equals 1 equals 1 equals Re. Similarly Re C equals C, 1, 1 equals 1 equals 1 equals 1 equals 1, 1 equals Re A. Hence asterisk C equals C asterisk equals, so that asterisk equals BA. By the polarized identity A2 equals so LL equals A2. Applied to 1 this gives R asterisk A equals A2. Replacing A by R asterisk gives the other identity. Substituting the formula for R asterisk in LL equals L gives L2 equals L. Classification: it is routine to check that the real numbers are the complex numbers C and the quaternions H are examples of associative Euclidean Hurwitz algebras with their standard norms and involutions. There are moreover natural inclusions RCH. Analyzing such an inclusion leads to the Cayley-Dickson construction, formalized by A.A. Albert. Let A be a Euclidean Hurwitz algebra and be a proper unital subalgebra, so a Euclidean Hurwitz algebra in its own right. Pick a unit vector J in A orthogonal to B. Since C equals 0, it follows that J asterisk equals minus J and hence J2 equals minus 1. Let C be subalgebra generated by B and J. It is unital and is again a Euclidean Hurwitz algebra. It satisfies the following Cayley-Dickson multiplication laws. To check this, note that B and Bj are orthogonal, since J is orthogonal to B. If A is in B, then Ja equals or asterisk J, since by orthogonal 0 equals 2 equals Ja minus O asterisk J. The formula for the involution follows. To show that Bj is closed under multiplication, note that Bj equals Jb. Since Bj is orthogonal to 1, asterisk equals minus Bj. B equals J since equals 0, so that, for x in A, x equals J equals minus C asterisk equals minus J, x asterisk equals J, x. B equals J taking adjoints above, equals minus C asterisk B since equals 0, so that, for x in A, x equals minus x asterisk Bj equals J equals minus. Imposing the multiplicativity of the norm on C for a plus Bj and C plus Dj gives, which leads to hence D equals C, so that B must be associative. This analysis applies to the inclusion of R in C and C in H. Taking O equals HH with the product and inner product above gives a non-commutative non-associative algebra generated by J equals. This recovers the usual definition of the octonions or Cayley numbers. If A is a Euclidean algebra, it must contain R. If it is strictly larger than R, the argument above shows that it contains C. If it is larger than C, it contains H. If it is larger still, it must contain O. But there the process must stop, because O is not associative. In fact, H is not commutative and O equals J in O. Theorem. The only Euclidean Hurwitz algebras are the real numbers, the complex numbers, the quaternions and the octonions. Other proofs. The proofs of Lie and Chevalier use Clifford algebras to show that the dimension n of A must be 1, 2, 4 or 8. In fact, the operators L with equals 0 satisfy L2 equals minus A2 and so form a real Clifford algebra. If A is a unit vector, then L is skew-adjoint with square minus I, so n must be even. The real Clifford algebra and its complexification act on the complexification of A, an n-dimensional complex space. Since n is even, n-1 is odd, so the Clifford algebra has exactly two complex irreducible representations of dimension 2n, 2-1. So this power of 2 must divide n. It is easy to see that this implies n can only be 1, 2, 4 or 8. The proof of Ekman uses the representation theory of finite groups, or the projective representation theory of elementary abelian two groups, known to be equivalent to the representation theory of real Clifford algebras. Indeed, taking an orthonormal basis A of the orthogonal complement of 1 gives rise to operators E equals L. Satisfying this is a projective representation of a direct product of n-1 groups of order 2. The operators UI by construction are skew-symmetric and orthogonal. In fact, Ekman constructed operators of this type in a slightly different but equivalent way. It is in fact the method originally followed in Hurwitz. Assume that there is a composition law for two forms where Z is bilinear in X and Y. Thus where the matrix T equals is linear in X. The relations above are equivalent to writing the relations became now set Vi equals TT. Thus Vn equals I and the V1. Vn-1 are skew-adjoint, orthogonal, satisfying exactly the same relations as the UIs. Since Vi is an orthogonal matrix with square minus I on a real vector space, n is even. Let G be the finite group generated by elements Vi such that where epsilon is central of order 2, the commutator subgroup G is just formed of 1 and epsilon. If n is odd, this coincides with the center, while if n is even, the center has order 4 with extra elements gamma equals V1, Vn-1 and epsilon gamma. If G and G is not in the center, its conjugacy class is exactly G and epsilon G. Thus there are two n-1 plus 1 conjugacy classes for n odd and two n-1 plus 2 for n even. G has G equals 2n-1 one-dimensional complex representations. The total number of irreducible complex representations is the number of conjugacy classes. So since n is even, there are two further irreducible complex representations. Since the sum of the squares of the dimensions equals G, and the dimensions divide G, the two irreducibles must have dimension 2 halves. When n is even, there are two and the dimension must divide the order of the group, so is a power of 2, so they must both have dimension 2 halves. The space on which the Vi's act can be complexified. It will have complex dimension n. It breaks up into sum of complex irreducible representations of G, all having dimension 2 halves. In particular, this dimension is n, so n is less than or equal to 8. If n equals 6, the dimension is 4, which does not divide 6. So n can only be 1, 2, 4 or 8. Applications to Jordan algebras. Let A be a Euclidean Hurwitz algebra and let Mn be the algebra of n by n matrices over A. It is a unital non-associative algebra with an involution given by the trace Tr is defined as the sum of the diagonal elements of X and the real valued trace by Tr equals ReTr. The real value trace satisfies. These are immediate consequences of the known identities for n equals 1. In A, define the associator by it is trilinear and vanishes identically if A is associative. Since A is an alternating algebra, B equals 0 and B equals 0. Polarizing it follows that the associator is antisymmetric in its three entries. Note also that A, B or C lie in R, then the A, B, C equals 0. This implies that M3 has certain commutation properties. In fact, if X is a matrix in M3 with real entries on the diagonal, then whether in A. In fact, if Y equals X, X2, then since the diagonal entries of X are real, the off-diagonal entries of Y vanish. Each diagonal entry of Y is a sum of two associators involving only off-diagonal terms of X. Since the associators are invariant under cyclic permutations, the diagonal entries of Y are all equal. Let Hn be the space of self-adjoint elements in Mn with product xy equals 1/2 and inner product equals TRR. Theorem. Hn is a Euclidean Jordan algebra if A is associative and n3, or if A is non-associative and n equals 3. The exceptional Jordan algebra H3 is called the Albert algebra after AA. Albert. To check that Hn satisfies the axioms for a Euclidean Jordan algebra, note that the real trace defines a symmetric bilinear form with E equals Xij2, so it is an inner product. It satisfies the associativity property equals because of the properties of the real trace. The main axiom to check is the Jordan condition for the operators L defined by Li equals xy. This is easy to check when A is associative, since Mn is an associative algebra, so a Jordan algebra with xy equals 1/2. When A equals 0 and n equals 3, a special argument is required, one of the shortest being due to Freudenthal. In fact, if T is in H3 with TRT equals 0, then defines a skew-adjoint derivation of H3. Indeed, so that polarizing yields. Setting Z equals 1 shows that D is skew-adjoint. The derivation property D equals dy plus xd follows by this and the associativity property of the inner product and the identity above. With A and N as in the statement of the theorem, let K be the group of automorphisms of E equals Hn, leaving invariant the inner product. It is a closed subgroup of O, so a compact Lie group. Its Lie algebra consists of skew-adjoint derivations. Freudenthal showed that, given X in E, there is an automorphism K in K such that K is a diagonal matrix. Freudenthal's diagonalization theorem immediately implies the Jordan condition, since Jordan products by real diagonal matrices commute on Mn for any non-associative algebra A. To prove the diagonalization theorem, take X in E. By compactness, K can be chosen in K, minimizing the sums of the squares of the norms of the off-diagonal terms of K. Since K preserves the sums of all the squares, this is equivalent to maximizing the sums of the squares of the norms of the diagonal terms of K. Replacing X by Kx, it can be assumed that the maximum is attained at X. Since the symmetric group Sn, acting by permuting the coordinates, lies in K, if X is not diagonal, it can be supposed that X12 and its adjoint X21 are non-zero. Let E be the skew-adjoint matrix with entry A, entry minus O asterisk in 0 elsewhere, and let D be the derivation ad T of E. Let Kt equals EXPTD in K. Then only the first two diagonal entries in X equals KTX differ from those of X. The diagonal entries are real. The derivative of X11 at T equals 0 is the coordinate of T, X, i.e., a asterisk X21 plus X12 are equals 2. This derivative is non-zero if A equals X21. On the other hand, the group Kt preserves the real value trace. Since it can only change X11 and X22, it preserves their sum. However, on the line X plus Y equals constant, X2 plus Y2 has no local maximum, a contradiction. Hence X must be diagonal.